Is Chapter 4, Section 2 of Timberlake Basic Chemistry, and today we're going to be looking at the periodic table. So the periodic table was developed over a number of decades, actually years, primarily put together by a man named Mendeleev in Russia about 1860s. So people have known that there has been patterns that you can see among the elements forever. Everybody that has studied them realizes that certain elements kind of react the same way, and that there is patterns among substances. But when you assemble all of the stuff that people know about in some kind of a logical way, lots and lots of information can be put through. So it is the cheat sheet of all time. It's one of the coolest things in terms of how much information you can get. If you had any idea, just looking up the periodic table, what it's telling you, you would realize that a lot of information is packed into a small place. So let's look at some of these details. It's in a table, okay, so it's in a graph or it's in a chart. So just with some vocabulary, a group is any elements that's in a column. So a column is going to have similar chemical properties. So if something reacts with water, anything in that same group is going to react with water. If something reacts with acid or melts in acid, anything in that group should in different degrees show those same properties. So group is a vertical column. A period, the reason why it's called a periodic table, is a period is a horizontal row. And a period is something repeatable. So in a school you would have a first period and then a second period where the bell rings and you begin class and then you go to the end of a period, then the next period starts. So it's something repeatable. So as you proceed from the left to the right across a row in a periodic table, the chemical properties change because you're passing from one group to another. So you're seeing a change in chemical properties as you go from one element to another because something is similar about everything that you're passing through as you're going across it, because there's patterns among substances. So here is group 2, and here's period 4. So you can see that that's just vocabulary term. Now, you've got different kind of groups here. If you look at this periodic table, I have group 1A, and then group 3B, 4B, 5B, and then it comes back up to 3A. So the groups are not always the same. And you're going to see that where a group is often will determine the chemistry of what's going on. So I think of the valleys as being transition elements, and the hilltops, either the skinny hill at the front, the first 2 columns, and the last 6 columns at the mountaintops as being more representative elements. And we'll get to the details later. So you can name them either 1 to 18. So the periodic table in my classroom is simply labeled 1 to 18, and you deal with those columns as you learn how they work. The older style, which I think is extremely useful, is to name the first 2 and the last 6 as 1 through 8A, and all of the valleys as B's. And what that means is that the first 2 and the last 6 columns, or first 2 and the last 6 groups, have something very in common, and that is that you have the valence electron is beginning to fill from 1 through 8. So the first group would have 1 valence electron, the second group, 2A, would have 2. Then when you get to the other side of the periodic table, the beginning of that hill would be group 3, has 3. Well, you have 10 elements in between that essentially you ignore, and those are transition elements because those electrons are not on the outer shell, but they're actually in an inside shell. So if you see here, group 1 has 1 electron in its outer shell, group 2 has 2, and then when you skip all the transition elements, the next one that would have 3 in its outer shell is 3A, or 13. So those have something in common as well. So you kind of separate in your mind, why do the first 2 and the last 6 have something in common, and these transition are separate, thought of in a different way. So group 1 has a name, and it's called the Alkali Metals. And alkali just means basic as opposed to acids. You have acids and bases. If you put a metal in water, it reacts with that water, and when it does, it turns the water from an acidity level that's low, like an acid, way high up to a alkali or a base. So it turns the water to having a high pH. Group 7 is called the halogens, and the halogens are extremely reactive. They're mostly gases, and these halogens are one away from having a full valence shell, and for that reason they're extremely reactive. Another difference in the periodic table in terms of where they are has to do with the staircase, and the staircase from boron down to astenine is called the metalloids, or the semi-metals. So anything to the left of that staircase is going to be called metals. The non-metals are in the upper right corner, and then the metalloids, or the semi-metals, are on the staircase between. Now aluminum is touching the stairs but is considered a metal, and also hydrogen, which is in column 1, is considered a non-metal. So metals are very shiny, they're conductors of heat, they're conductors of electricity. Non-metals are usually brittle, like sulfur, like a powder. Very poor conductors of electricity, but good conductors, or good insulators, so the electricity doesn't pass. And then metalloids are that perfect sweet spot. So a lot of times computer chips are made out of metalloids. So you can see that you've got a difference between a non-metal, a metal, and a metalloid in terms of how can you pull it into a wire, or can you hammer it into a sheet? That would be a metal. You couldn't do that with a crunchy powder. It would be impossible. A non-metal, you could kind of tweak it. You can see that electricity will pass or not pass, heat will pass or not pass. There's some differences between them, and you can use those differences to your advantage when you are making something. So very, very basic introduction. I know I didn't give you a lot of information, but I hope that this helped in some way.